Trace and determinant invariance. The hidden beauty of matrix diagonalization via similarity transformations. In our problem today, A.28, we're told to let T equal some complex valued 2 by 2 matrix as seen here. In part A, we wish to verify that T is Hermitian. In part B, find its eigenvalues. Note that they are real, which is true for any Hermitian matrix. C. Find and normalize the eigenvectors. Note that they are orthogonal, also characteristic of Hermitian. D. Construct the unitary diagonalization matrix S and check explicitly that it diagonalizes T. And then in part E, check that the determinant and trace of T are the same for T as they are for its diagonalized form. So this will be a big talking point. So, for part A, for a matrix to be Hermitian, it must satisfy the condition that the Hermitian conjugate is equal to the matrix itself. As such, all we have to do is check and see that we have T dagger, which is the transpose conjugate. As we see the dagger or the tilde, the transpose switches the off coordinate or off main diagonal terms. It flips the rows and columns. And as you see, we get a 1 minus I, 1 plus I in the alternate spots, but then the conjugate comes in and switches the signs on the i's, so we restore our T matrix. Very cool. And then in part B, to get the eigenvalues, we have to go back to our old handy friend, the characteristic equation, which we know is the determinant of T minus lambda I, all that equals 0. So here we have to simplify our matrix inside the determinant, and we're good to go. This being a 2 by 2, we just need to take this component, multiply to this, minus this component, multiply to this, and we see that we get a quadratic equation. From there, we see that once we simplify out by distributing these, we get the cross terms, which are the i's in this case, to cancel. This I square will go to a -1, so we're good to go there. And now we just have a quadratic that can be factored after simplification. So we see that our eigenvalues are 2 and -1. And it's important to note for this problem specifically that these are non-degenerate eigenvalues. So to determine the eigenvectors, we have to substitute each of these distinct eigenvalues back into the characteristic equation. And we've seen this play out before, so we have lambda 1 here on the main diagonal. V1 is the eigenvector composed of A1 and A2 respectively. And then from there, we see that we need to go ahead and plug in our first eigenvalue, which is 2 in this case. Take the difference, simplify this down, set that equal to 0. Now, because this is equal to the 0 vector, technically, this is a homogeneous system of linear equations, and we can solve it via Gaussian elimination. As such, here are the row ops for the simplification. We want to simplify that down, and then we're good here. Then we're going to take these with the common factor of 1 plus I, which is, we see that this row multiplied by this constant, we'll get rid of that. So we end up with the redundant row because this row simplifies to all zeros. Now what this says is that 1 times the first component of the vector plus -1 plus I times the second component equals 0. Solve that for the first component and we see that we get 1 minus I a sub 2. Easy enough. So the general solution then, once we substitute in the values for A1, is we get the vector of the form 1 minus I and 1 with some free parameter A2. Now this A2, we can just make it a convenient value and set it equal to 1, so that's what we do. Repeating these for the other two, or the other eigenvalue rather, we see that lambda 2 can fit in just perfectly fine. Now we'll label V2 with B1 and B2 components, so we're good to go there. Moving forward, Gaussian elimination again. Again, the PDF has all of this written out. And then we see we have B1, all this fun stuff. This is going to get gross very soon. But we see that we have a free parameter for B1 in terms of B2. So our general solution takes the form of this. Now, with this free parameter, with this 1/2 right there, it only makes sense to set the free parameter 2, and then we get a easy to read vector with I minus 1 over 2, with the second component 2 rather. So eigenvectors, we've seen this before, and we'll just go ahead and continue with it. So, of course, being a quantum mechanics appendix, we need to normalize these eigenvectors for the general solutions. So let's go ahead, normalize V1. We see that splitting out these cross terms here, the negative I and positive I will cancel, but then we get plus I here, minus I here. That'll lead to a minus minus 1, so the negatives cancel, so we're leaving with 1 plus 1 out of those two brackets, and 1 times 1 from here gives us a 1 here, so we're good to go. That all comes to square root of 3. Easy enough. So here's our normalized vector. Run that through for V2. We see we get 1, 1, 4. All adds up to 6, so our normalization is 1 over root 6. Good to go. Now, we have to verify orthogonality of these things, because again, we're told that these span the space, so if that's the case, these should be linearly independent and hence orthogonal. So if we run this through, we see that the cross terms will cancel. I cancel. This I squared that's positive goes to -1. -1 here, -1 from here, add together to give us the -2 here. So -2 plus 2, we see that that goes to 0, so we are indeed orthogonal. That's good to know. And since that was a lot to deal with, let's summarize all our eigen decomposition. We see that for lambda 1 equals 2, we get V1 that is normalized as such. And for the next part, we are going to want to distribute this 1 over root 3. That's what we see here. Same thing for lambda 2 equal -1. We see our normalized eigenvalue or eigenvector here. And so distributing that into component-wise, we're good to go. Note that apparently this doesn't like uploading well, but that's a parentheses around those components. This is a skewed fraction, so it's not just over 1 or under 1, it's under the whole thing. So a little bit of formatting error there on my part, but you get the idea. Alright, so diagonalization. Now, I wrote quite a bit about this in the PDF for the patrons because working from book to book to book, it all kind of comes together in one form, but we have different notations and where do we put the inverse matrix, where do we put the non-inverted matrix. So what this comes down to is that we really need the rows or the columns of the invertible or unitary matrix to be the eigenvectors. And that's what we see here. So in this book's notation, that's S inverse. In the linear algebra books, it's called P. Okay, so they both come from the same spot. What they do is they use the eigenvectors that are, in this case for quantum mechanics, are normalized as the columns for the matrix. So eigenvector 1, eigenvector 2. Now, since this is unitary, we know that we have P inverse equals P dagger. Okay, so that's how we get S out of this thing. And from that, we just take the transform, we take the conjugate transpose, and we see that the green now is the row instead of the column. And these i's have a plus or a minus respectively, thanks to the conjugate. So now we're left with proving that these two matrices via the similarity transform. As we see here, we have S, T, and then we have S inverse for the similarity transform. Run this through. What do we get? Sure enough, after a couple matrix multiplications, we are good to go. We see that we restore the fact that we get a diagonal matrix 1, and that the diagonal entries are the eigenvalues. So this, again, is freaking amazing, and we're going to see why it's amazing in the next section. So trace and determinants. So if we look at this, the similarity transform is remarkable because it's said to be invariant with respect to trace and determinants. So now we have to verify that. Now our trace again is just the sum of the main diagonal terms, in this case 1 and 0. Thankfully the complex numbers are off diagonal. So 1 plus 0 gives us 1, easy enough. We see here our determinant in the standard 2 by 2 form, 1 times 0 right there. This times this with a minus sign there. Distribute that out, we get -2. Now, as a little side quest to this can also be found from the eigenvalue equation by setting lambda equal to 0. And so as you see, our characteristic polynomial came from the eigenvalue equation where we had t minus lambda I. But since we're looking for det t, setting lambda equal to 0 gets rid of this part of it, and we just get det t. That being said, setting lambda equal to 0, we get determinant t, 0, 0 here, cancel, we're left with -2. Sure enough, that's the same thing here. So however you want to find the determinant or whatever tools you want to use, this just verified the last part of equation A92, so we could use both routes. Personally, using this second route is easier and quicker since we already went through the hoops of determining the eigenvalues, so this would be a much quicker route to the determinant. Now, where the actual part and the heart of this question is coming from is in the diagonalized form from the similarity transform. So the trace here, again, we need to add the main diagonal component. So we have 2 plus -1. That's just 2 minus 1, so that ends up with 1. Note 1 and 1, same thing, although different form. The determinant of the diagonalized t, crisscross, as we see color-coded. Then we see we get -2 again. So either way, we show that the trace of t is equal to 1, which is also equal to the trace of the diagonalized t. And similarly for the determinant. Both determinants equal -2 and we are good to go. This verifies that the similarity transform has invariant properties. And as such, there's actually an entire list for this. So these are called similarity invariants, and we see that for properties like the determinant, which we just showed, the trace, which we just showed, but we also have invertibility rules, right? We also have rank and nullity rules, and these two things come into account more for the math side of things where we're verifying solutions. We know what to expect out of solution spaces, things like that. Characteristic polynomials, we have the same characteristic polynomial. That comes directly from the eigenvalues being the main diagonal elements of the diagonal forms. And then we see the eigenspace dimension. So here we go. This all comes full circle, and this is why we like it. Clearly, with these invariants, it makes it much easier to work with the diagonalized forms throughout everything else versus keeping it running with that chunky matrix. So that was a lot of fun. This again is for the non-degenerate spectrum of eigenvalues, but we will see the degenerate case next question. As you can tell, the diagonalized forms are very, very, very important to us. So that's why we like using them. Time is running out here at the lobby, so I will just say thank you to everyone for watching. I appreciate all the feedback, interest, and investment that the patrons and other subscribers have shown to me, and the clarity of thought that you have given within the scope of this year, because it has been crazy. So that being said, it's been a pleasure working with everybody. Please, if you want, support the channel by liking, subscribing, and sharing. And if you can, check out the Patreon page and the collections over there, because that's where all this work is written up and shared to. As always, thank you for watching, and until next time, stay curious.